Hi, welcome back to our third video for 2.7 inverse of a function. In this video, we're going to look at a real-life application for inverse functions. So as you can see here, there are a couple graphs that are shown. These graphs have to do with the speed that a car can travel and its corresponding stopping distance. So as you can see from this graph right here, if you think about a vehicle, as that vehicle increases speed, its stopping distance also increases as well. Okay, so the faster that you're traveling a vehicle, the larger the stopping distance will be. So if you're going 40 kilometers an hour, your stopping distance is 10. So that's the minimum stopping distance you could have if you're going 40 kilometers an hour for this vehicle. Okay. Stopping distance will depend on like how well the brakes are made, how good the tires are, and even the conditions of the road. But if all of that is perfect for this vehicle at 40 kilometers an hour, this is the minimum stopping distance. Okay, if you're going a little bit faster, 60 kilometers an hour, notice what happens to the stopping distance. It's now even a bit higher. It's like 20, maybe about 22 meters. So just by adding 20 kilometers per hour, the stopping distance doubles. Okay, so we can see that speed really influences the stopping distance for a vehicle. Now, if I was an engineer and I was using this graph, I would have to be a little bit careful how I use it, and I want to make sure that I interpret everything properly because if the speed is 40, I don't want to say the stopping distance is at most 10 meters because I know the stopping distance can't be any smaller than 10 if I'm going that fast. So it would be better for me to look at this graph over here instead. This kind of makes a little bit more sense. So and notice what's happened is the X and Y axis has switched compared to what it was on this graph. So by switching the axes, I can now say, okay, if I had a stopping distance of 10, how fast could my car go? And I would read the graph and I would say, okay, about maybe 58 kilometers per hour or less. That's how fast the car could go. So I feel like this curve makes a little bit more sense when you're thinking about the context of the situation. So um, I would rather read the stopping distance and then know how fast the car could go, the maximum speed. Okay, this equation is governed by this function. So, and this one right here, we have this equation, d equals 0.006 v squared. So we can see it's like our x squared graph, except it's been vertically compressed by a factor of 0.006. That's why you can see it's really compressed. So then to get this graph here, if they switch the x and y axis around, it's like they rearranged this equation and that they isolated for v. So when you're dealing with real life context situations and you're trying to show the inverse, what you want to do is you just want to rearrange the equation. You don't want to switch d and v because what that's going to do is it's actually going to create a new equation and it's actually going to change the data. It's going to change the relationship between the two variables. So in real life context situations, when you're finding the inverse, we actually just want to isolate for the other variable. We don't want to do any switching around. We'll talk about that a little bit more later. Okay, so part A, it says state the domain and range of the function d. So this function here, we can look at this graph and we can state the domain and range. So we'll do this in blue. So our domain and range. So our domain, we're now looking, when I look at this equation, the domain has to do with the speed, v. Okay? So I want v to be a positive value. If you look at the graph, we're not looking at when the speed is negative. So we want speed greater than or equal to 0. So I can say the speed is an element of R and that the speed is greater than and equal to 0. Okay. So this is only because speed must be positive. Okay. Now the range, well, for this graph, I'm now looking at the stopping distance. That's the value d. So it's everything from 0 up. So we can say d is an element of R, and d is also greater than or equal to 0. Okay. So distance cannot be negative, right? Okay, so that's for part A. Part B, it says determine an equation for the inverse of the function. Okay, state its domain and range. So there's our equation. We want to find the inverse. So like I said, let's just write this out first. 0.006 v squared. So for real life context, to determine the inverse relationship, oh, let me rewrite that there. To determine the inverse relationship, we just want to solve for the dependent variable. Okay, this is because the cause and effect relationship between the two variables cannot change. Okay, so we'll say, so you cannot just switch D and V. Okay, so let me just kind of explain that a little bit. So this equation, right, corresponds to this graph. So this shows the stopping distance versus speed. So let's just take 1 point out of here. That's maybe a little bit, try to get something a little bit obvious. So we'll just say, let's say this one here. Okay, so if we're going 40 kilometers per hour, that corresponds to a stopping distance of, let's say, 9 meters. Okay. Now, when I find the inverse, okay, I want it to, the way how I want it to work is I want it to go 9 meters, 40 kilometers an hour, right? I want that to be the inverse. So what I don't want to do is I don't want to keep the units. I don't want it to say 9 kilometers per hour corresponds with 40 meters stopping distance. That doesn't make sense. So that would be wrong if we did that. So all I want to do is just kind of have those switch places. So like giving us this graph right here. That way the cause and effect still holds true. Okay. So in order to do it that way, when we algebraically try to find the inverse, we don't want to switch D and V. If we switch D and V, that would be like switching the units too, and having 9 kilometers per hour with a stopping distance of 40 meters. That would be kind of ridiculous, and it would actually be really inaccurate. So only for these real life context questions, we don't want to change the cause and effect. So all we do is just isolate for the dependent variable. So yeah, just isolate for the dependent variable. That's it. Okay. So this will actually be quite easy. When we have the equation d equals 0.006 v squared, sorry, that is an equal sign. I know it kind of looks like the domain colon. Okay, so d equals 0.006 v squared to solve for v. So what we can do first is divide both sides by 0.06. Okay, and then v squared, to reverse the square, we can square root both sides. So we'd have d over 0.006. Okay. Now, because we don't want any negative values for speed, we're going to just keep the positive value of this. We don't need to do the plus or minus, okay? Because it's a real life context for this question. Okay, so that would be our inverse equation for this. We also need to find the domain and range. So the domain, we're going to say D is an element of R, and we only want positive values for the domain. So the domain should be greater than or equal to 0. So looking inside this equation, I want this to always be positive. And then the range, this is going to be the speed. Speed is an element of R. And the speed, we also only want positive values for that too. Okay, that's why when we set up this domain and range, we're actually restricting this equation to only have the positive values, not any of the negative ones. Okay, and that was our last example. And I hope you found these videos helpful, and I'll see you guys later.